So we'll continue with the numericals of chapter 6. So we'll be continuing with the problems of chapter 6. And as we had followed a procedure where I'll give you a few minutes to attempt the question on your own, and then we'll look at the solution. So we'll continue with that. The upcoming problem is slightly different problem in the sense that you'll have to use the tables in this problem also, and you'll have to do the interpolation also. So kindly first go through the problem statement, which states that a refrigerant R134A, uh, specified over here, so I know which tables to use. It enters the evaporator coils placed at the back of a freezer section of a household refrigerator at 120 kilopascal with a quality of 20%. So this is the condition. The refrigerant is essentially entering into the evaporator, and it leaves at the same pressure, which is 120 kilopascal and 20 degrees centigrade. It further says if the compressor consumes 450 watt of power and the COP of the refrigerator is 1.2, you have to determine the mass flow rate of the refrigerant and the rate of heat rejected to the kitchen air. So I'll just give you a quick uh, schematic of the refrigerator. You have a condenser, again the four component, which is rejecting heat Q dot H to the kitchen. This is the high temperature reservoir. The expansion valve, which is acting as a pressure and temperature reducer. Then you have the refrigerant entering into the evaporator at this condition. This is state 1, and as it leaves through the evaporator, it is at state 2. During this process, the refrigerant absorbs the heat at the rate of Q dot L, and furthermore it goes through the compressor, which is providing the work into the system at a rate of 450 watt. Now, sorry, sorry, is there a problem? All right. So you have to determine the mass flow rate of the refrigerant. Now I'll give you a hint. I'll leave you with a hint of that Q dot L, that is the rate at which heat is absorbed in the evaporator. It is essentially equivalent to the mass flow rate of the refrigerant multiplied by QL. You can refer to it as capital Q, but this QL refers to the energy absorbed kilojoules per kg per unit mass. So this is the expression. You have to find this property, and you have to look into these two. You have to find out these two from the data given, and that would, these Q dot L and small ql, they will lead towards the mass flow rate of the refrigerant, which is the first part. So I'll leave it for you to find out both the properties, and I'll give you few minutes for that, and then I'll move on towards the solution. Remember, you have to use the refrigerant tables in this, and this would require interpolation. Cumbersome interpolation process is involved. We'll go through that, but try to attempt it in the first place. Are you attempting this? Are you finding out the properties?
Sir, QL की वैल्यू सर COP मल्टीप्लाइड बाय the work net in होगी.
Simple enough, yes. So
Yes sir.
Q dot L, that is the rate. Since you are talking about, this is rate. COP of refrigerant is essentially Q dot L over work dot in. So if the COP of a refrigerant is 1.2, Q dot L you need to find out, and work net in is essentially 450 watts. That means Q dot L would be 1.2 times 450 watts, which would be
540.
40 watts or 0.54 kilowatts. Clear enough?
Sir,
Is it
mass
clear?
flow rate 2.6.
Sorry, what is the answer for mass flow rate?
Sir, 2.6.
2.6 what?
2.6 kilogram per second.
2.6 what? 2.62
2.62, yes.
kilograms per second. All right. Who is this?
Is her.
Izhar. All right. Let's see, Izhar, whether you found it correct or not, because it requires extensive interpolation. Now, you have found out Q dot L. You have to find out the mass flow rate of the refrigerant. So you need to find out small QL or kilojoules per kg through the evaporator. In order to find out QL through the evaporator, you have to take the difference between the enthalpy of the two states, H2 minus H1. Though it is not W dot plus Q dot, it is the difference of the enthalpies at the two states that would give you the heat uh, transfer through the system. If you apply the energy balance on this evaporator as a component, if I have this evaporator as a component and I apply E in equals to E out, so the energy coming into the system is essentially what? What is coming into the system? No work is coming into the system, heat is coming into the system. It has Qn, and there is a refrigerant that is moving into the system with an enthalpy of H1, and there is a refrigerant that is moving out of the system with the enthalpy of H2. The potential energy, kinetic energy, and work essentially are zero. So E in equals to E out. E in, you have Q in plus H in, H1, and E out. So the heat that is coming is essentially the difference of H2 minus H1. This is the enthalpy this is the heat that is coming into the system, heat per unit mass. So now I have to find out the enthalpies at the two states in order to find out the heat transfer per unit mass. In order to do so, the first condition that has been given to me is that for H1, I have been given that the pressure is 120 kilopascal and the X1 value is 0.2. This is the quality value, and H1 is essentially HF plus X times HFG. This means I'll have to go to the R134 table. My pressure is 120 kilopascal. HF value is 22.49 plus X is 0.2, which is multiplied by HFG, which is 214.48. 214.48. So this value comes out to be, can you find out the value for me? G, can you find out the value?
65.386.
So it is
Sir, 65.3.
65.386.
Yes, sir.
All right. This was the easier part, where you had to find out the enthalpy of the inlet state or the state at which refrigerant is entering into the system. The problem comes now for state 2. You have the pressure as 120 kilopascal or 0.12 megapascal, and your temperature is this is minus. Temperature is minus 20 degrees centigrade. So for 120 kilopascal, minus 20 degrees centigrade. What is the region?
Plus
Saturated.
20.
Sorry,
Plus 20 degrees centigrade.
minus 20 degrees centigrade.
Supercooled region.
Supercooled?
Saturated.
Sorry,
Saturated, sir.
saturated mixed region.
Yes, sir.
All right, let's see how we can find it out. You have versus specific volume plot, and this is the dome. Your pressure is
Sir,
120.
supercooled में.
Let's see, your
So
pressure is 120 kilopascal. At 120 kilopascal, your temperature, saturation temperature is minus 22.32. So this is minus 22.32, this temperature. The temperature of my system is minus 20 degrees centigrade. Would it be, if the temperature is increasing upwards, would it be upwards or downwards? This temperature is minus 22.32. Where would be minus 20? Above this line or below this line?
Below.
Minus 22.32 and minus 20. Minus 20 would be above this line.
Above.
Simple enough. This is minus 20 degrees centigrade. So is it clear to you which state my system is in?
Yes, sir.
All right. So I'll go to the table of superheated refrigerant, and once I go to the table, I find out that this is the table. In this table, the problem is we don't have the table for 0.12 megapascal. So what should we do? We have 0.10 megapascal and we have 0.14 megapascal, but we don't have 0.12 megapascal. What should we do? Sorry?
interpolation.
Yes, you'll have to do interpolation. All right, you have to do interpolation, and you will have to do interpolation for minus 10 degrees centigrade first, 0 degrees centigrade, and then you will be able to do it for minus 20. So how you will do that is the first thing is for minus 10 degrees centigrade, you will have the value of 0.10 megapascal. 0.12 you have to find, 0.14 you will take from the table. So 0.10 for 0.10 megapascal, the value is 247.49. 247.49. 0.12 megapascal you have to find out. 0.14 megapascal, it is 246.36. So for this case, you have to find out the value of X, which is 0.1 minus 0.12 over 0.1 minus 0.14 is essentially equal to 247.49 minus X divided by 247.49 minus 246.36. Can you help me find out the value of X?
246.925.
Sorry?
246.925.
Temperature minus 20 is.
Sorry, temperature, this is minus 10 degrees centigrade. We are first doing it for minus 10 degrees centigrade. 246.925, thank you जी. Yes, what is your question, Izhar?
सर मैं क्वेश्चन है कि ये तो आप minus 10 में ढूंढे, मतलब minus 20 नहीं है?
Yes, but do you have any value for 0.14, the enthalpy value for 0.14 at minus 20 degree centigrade? यहाँ पे कोई वैल्यू है आपके पास जिसके थ्रू आप इंटरपोलेट कर सकते हैं?
No, sir.
So first what you'll do is that you'll find out the value of X for 0.12. Then you'll do the same for 0 degree centigrade. And with these two values, X and Y values, you will interpolate it for minus 20 degrees centigrade. Got the point?
Okay, sir.
So 0.10 again, 0.12 and 0.14 megapascal. For 0.10 0 degrees centigrade, the enthalpy value is 255.58. For 0.12, you don't have any value. For 0.14, so you assume it Y. So 0.14 megapascal, you have the value of 254.60. Now with this, you'll do the interpolation again. 0.1 minus 0.12 divided by 0.1 minus 0.14, which is equivalent to 255.58 minus y whole over 255.58 minus 254.60. So can you find out the value of y for me?
255.09.
Very good. 255.09 kilojoules per kg. Now, since you have the two values available for you for the given pressure, now the third temperature is required. So what you'll do is that you will go for now minus 20 degrees. You'll now go for 0.12 megapascal. So for 0.12 megapascal, you have value of, you need to find out the value for minus 20, you have for minus 10 and 0 degrees centigrade. Minus 20, the value would be H2. Minus 10, the value is X, which is 246.925. And for 0 degrees, it is 255.09. So again, you will do the interpolation for minus 20, and how you'll get the value, you'll have minus 20 minus 10, minus 10 would become plus 10, and minus 10 minus 0. So you have done first two values and then the second and third value. Similarly, you'll do H2 minus 246.925, and then you'll use the second and third values, 246.925 minus 255.09. Can you give me the value of H2?
So I think 238.76.
Yes, 238.75. 75 or 76, it's the same, so it's 238.76 kilojoules per kg. This was the most important part in this question. Otherwise, it's a very simple question. So now you have to find out H2 minus H1 to find QL. So QL would essentially become H2 minus H1, where H2 is 238.76 minus H1, you found out 65.386. So minus 65.386. This would give you what?
173.374.
173.374 kilojoules per kg. All right, now you have the Q dot L also given to you, which is 0.54 kilowatt, and QL is all small QL is also known to you. So the mass flow rate of the refrigerant would be Q dot L divided by QL, which is 0.54 kilowatts divided by 173.374 kilojoules per kg. This would give you what? the mass flow rate?
3.1 into 10 power minus 3.
Yes, 0.00311 kgs per second. So this is your mass flow rate. Clear enough? Is this clear to you?
Yes, sir.
All right. The second part
Yes, sir.
was to find out the heat rejected to the kitchen air, which is Q dot H. And you know that if you apply the energy balance on the refrigerator, for refrigerator, work dot in plus Q dot L is essentially equivalent to Q dot H. So your Q dot H would essentially be equal to work dot N, which is 450 plus Q dot L, which is 540 watts. So this would become altogether as 990 watts or 0.990 kilowatts. So this would be your part B. Clear?
Excuse me, sir. Can you summarize this overall in few?
Can I summarize this overall? Why? Where
Yes,
were
sir.
you?
No, sir, I was there. बस थोड़ा सा कंफ्यूजन हो जाती है कि ये डिफरेंट टेबल से कौन कौन से ये फाइंड करना है, किस तरह पता चल रहा है.
What I'll do is that how to start. All right. Let me remove this and show you the solution. All right. So the first thing was you found out the clear.
Yes, sir.
Then what you did was you at state 1, which is this state, you found out the enthalpy value using the HF plus XXG formula. Clear?
Yes, sir.
Then what you did was you went on to state 2. For state 2, this is the condition of state 2, 0.12 megapascal minus 20 degrees centigrade. Clear?
Yes.
But you don't have a table for 0.12 megapascal. It is in between 0.10 and 0.14. Clear?
Okay, sir.
So what you did was you took the temperature minus 10 degrees centigrade and using 0.10 and 0.14 you found out the middle value for minus 10 degrees centigrade. So for minus 10 degrees centigrade you found out the value at 0.12 megapascal for enthalpy, which is 246.925. Clear?
सही है सर.
You did the same for 0 degrees centigrade. Since you again don't have any value for 0.12 megapascal for 0 degrees centigrade, you did 0.1 and 0.14 values and you found out the middle value using the interpolation, which comes out to be 255.09. Clear?
सर ये हमने तीनों के लिए क्यों किए हैं, ये -10 और 0 डिग्री के लिए?
I'll tell you why. Because in order to interpolate the value for minus, also for where is it? Sorry. So in order to get the value for minus 0.12 megapascal and minus 20 degrees centigrade, you need to have at least two values, two temperature values at 0.12 megapascal to find out the third one. So minus 10 and 0 degrees, if you have the enthalpy value at these two temperatures, you can find out at the third temperature. Clear?
सही है सर. हम कोई और ले सकते हैं लाइक हायर वैल्यूज, मतलब -30 वगैरह या?
हाँ, ले सकते हैं, ले सकते हैं, ले सकते हैं. देखिए सबसे आसान तो ये होता, I'll show you, सबसे आसान तो ये होता कि if there would have been a value of enthalpy over here, let's say some value z, whatever value, तो आप सीधा सीधा काम क्या करते, you would interpolate between minus 20 degree centigrade. You'll say 0.10 पे वैल्यू है sorry for minus 20 degrees centigrade you say that 0.10 megapascal the value is 239.50. All right, 0.12 पे you need to find out H2 and 0.14 पे वैल्यू है, let's say ये वैल्यू कुछ भी है 240 something whatever 240, so you can find out using the interpolation. Clear?
Yes sir.
Is this clear to you?
Yes sir.
लेकिन चूंकि यहाँ पे वैल्यूज नहीं है, so what you did was you constructed the table for 0.12 megapascal. What you did was you found out the value for 10 degrees, you found out the value for 0 degrees, and then you found out the value for the XY values, then you found out the value for minus 20 degrees centigrade. Clear?
Yes sir, clear.
Okay.
Thank you sir.
Yeah. So what you did was you found out the value for minus 10 degrees centigrade, the corresponding value of enthalpy at 0.12 megapascal. You used 0 degrees centigrade and 0.12 megapascal to find out the corresponding value of enthalpy. And then now you have constructed your small table where for 0.12 megapascal you'll have a value of minus 10 at 0. So you'll use these values to interpolate the value for minus 20 degrees centigrade. Once you have the enthalpy value at minus 20 degrees centigrade, you just have to take the difference between the two values of enthalpy, H2 minus H1. This would give you the change in enthalpy or QL. You divide this QL by the Q dot L, and that would give you the mass flow rate as 0.00311 kgs per second. Clear enough?
Yes sir.
All right. And then you have the second part where you have to take the find out the rate of heat redirected to the kitchen air. That is simple enough. You have to apply the energy balance. Q dot H is essentially equal to Q dot L plus work net in, and you add the two values. This would give you 990 watts. I hope it is clear to you.
Yes sir.
All right. So what I'll do is that I'll stop over here since it's numerical has taken a lot of time. This is basically the purpose of this numerical was to go through this double or triple interpolation process. This was the goal. The rest it is easier. So I'll stop over here and have a break of 5-10 minutes and 5 minutes so that we can continue with the next part of the next numericals. All right.